we figured out a technique to calculate how much a galaxy weighs by looking at how fast things rotate around it. But before we can actually do this, there are a few little observational complications, and the one we're going to worry about first is deprojection. So let's take M33 as our example. What do we know about it? Well, we have an image, we have the stars and the gas further out, and we have the velocities of the gas. In this particular case, the gas on this side is moving towards us, away from us on this side. These measurements are made normally along the long axis. This is the long axis. It's the most elongated direction. So what this is telling us is the velocity in the center here is low, and the velocity is getting more and more positive as you go out this way, and more negative, but with the same values as you go down this way. And this point out here would be the extreme edge of the radio. And that leads us to our first problem. The galaxy, as you can see, is not a perfect circle. It's an ellipse. Probably the galaxy really is a perfect circle. The fact that it's an ellipse is because it's inclined, it's tilted to the line of sight. It's not perfectly face on. And that's going to affect our velocity measurements. Okay, imagine this is a galaxy. Now it's a disk, so it's flat in one dimension, round in the other. If it's face on, you can measure the radius, the diameter, straightforwardly. If it's inclined, say something like this, the longest axis of the ellipse from here to here remains the same, but the short axis from there to there is shrunk. In the extreme case, if it's edge on, the long axis once again remains the same, but the short axis has shrunk to almost nothing. If it's rotating, and it's face on, then you won't pick up any rotation because everything will be perpendicular to the line of sight. If we tilt it, you'll find that on one side it's getting close, it's going towards you, the other side it's going away from you. So you will pick it up. Okay, so what are we going to do about this? Well, if we see a galaxy that looks like a circle, we know it's face on, so we can measure its true shape properly, but we're not going to find any velocity because it's all perpendicular to the line of sight. As it gets more and more tilted, it will appear to be more elliptical. So the log axis will stay the same, but the short axis will get shorter until if it's really edge on, it will just look like this, and you won't see very much at all, but you'll get a full measurement of the velocity because it's now pointing straight towards and away from you. So here's what we're going to do. We're going to look at how elongated the shape is. And that will tell us what angle the galaxy is inclined at. Once we know the inclination angle, that will allow us to correct the velocities to work out the true rotational velocities. So how do we do this? Well, let's imagine we are over here. It's our eye, and we're looking at a galaxy, and it's inclined, tilted at some angle. So here's the direction from the Earth, and we'll call this angle here theta. Now the long axis will be this here, because that doesn't change. We'll call that L. But the short axis is going to be this distance here, S. And so the smaller theta is, the smaller S is, though L remains the same. So what actually is S? Well, that's very straightforward from trigonometry. We get S is just equal to L sine theta. So what we can do is if we can measure the short axis S and the long axis L, we get that the angle theta equals arc sine s over L. In this particular case, the short axis of M33 is 45 arc minutes, and the long axis is 73 arc minutes. Roughly, it's hard to measure. If you look at the image, you'll see the galaxy looks a bit fuzzy, but by and large, that is about 45 arc minutes. This is just the stars, is about 73 arc minutes. So this is arc sine 45 over 73. Doesn't matter what units are as long as they're consistent, because everything else will cancel out, which comes to about 38 degrees. Once we know that, we know that the velocity is going to be along here, either up or down in the plane of the disk. So that's the true velocity v. What we're actually measuring is the component of the velocity along the line of sight here. So that's a right-angled triangle. So v observed is going to be the true velocity times, in this case, cosine theta. So this is what we measure. And so the true velocity is the observed velocity over cos theta, and we've worked out cos theta up here. So this process is called deprojection. It allows us to work out the true velocities from the observed velocities, correcting for the tilt of the galaxy.